Welcome back to the series of Ancient Secrets of Prediction. This is a glimpse of the previous video, where we learned how to solve a system of three-variable equations using the elimination method. The variables were represented as apple, mango, and parking. The elimination method helped us solve the problem and determine the values of each variable. We also tried solving using the graphical method. Now we will learn how to automate this entire process using the code in Python. First, we will represent this same set of equations using the variables x, y, and z. We will now convert them into matrix form. A matrix is a rectangular arrangement of numbers organized in rows and columns, similar to a table. A system of equations can be represented using an augmented matrix, where each row corresponds to one equation in the system, thus giving us a 3x4 matrix having 3 rows and 4 columns. Here, the first column represents the x coefficients, the second column represents y coefficients, the third represents z coefficients, and the fourth represents constants. Now, we will divide the process into 2 parts, represented by 2 blocks of code. First, we will use the eliminate function to eliminate the variables as we go from top to bottom. The augmented matrix E will act as the input for this function. Here, top to bottom means that we work row by row, starting with the first row. It will give us the required matrix as the output. Then, we will pass the output to the solve-elimination function, which solves the variables from bottom to top. Bottom to top means that we start with the last row and move upward. When we reach the topmost row, we will have determined the value of every variable, giving us the solution. Does this sound confusing? Let's break it down in more detail to make it clearer. Here is the complete code for the eliminate function. To understand how it works, we must first go through the code step by step. E represents our augmented matrix. The I loop refers to the ith row of the matrix. Its value ranges from 0 to the length of the matrix E, which corresponds to the number of rows. In this case, the length of the matrix E is 3. Therefore, I equals 0, 1, and 2. We will not include 3 here because the for loop functions only when the condition I less than length of the matrix holds true. But why start from 0? In Python, the indexing starts at 0, so 0 represents the first index. The j loop refers to the jth row. Its value ranges from I plus 1 to length of the matrix E, which is 3. Both of these loops help us to follow the top to bottom approach and iterate over the matrix row by row. Mult refers to the multiplier constant. We will discuss its functioning later in the video. The k loop ranges from I to the length of ith row in the matrix E. Length of the row refers to the number of elements in a row, which corresponds to the number of columns in the matrix, which is equal to 4. Together, these loops systematically reduce the matrix to a simpler form by eliminating elements from subsequent rows following the elimination process. These are the indices for the rows and the columns. We will be using them to address the elements of the matrix. Now let's see the working of this code. In the first loop, I equals 0, which refers to the first row of the matrix. The value of j is equal to 1 and 2, as the for loop ranges from I plus 1 to len e. It means that when I equals 0, the j loop will run twice. First, j equals 1, which refers to the second row of the matrix. Don't get confused and remember that indexing in Python starts at 0. The goal is to eliminate the elements in the jth row. For this, the coefficients in both rows must be the same. So we calculate the multiplier constant by dividing the first element of the jth row by the first element of the ith row. Here, eji, which is e10 equal to 3, and eii, which is e00 equal to 1. Therefore, the multiplier constant comes out to be 3. Here comes our k loop. Its value ranges from 0 to 3 as I equals 0, and len ei equals 4. The k loop will multiply each element of the ith row by the multiplier constant, subtract it from the corresponding element of the jth row, and update the value simultaneously. At first, k is 0, so we will multiply eik, which is e00, by the multiplier constant, and subtract it from ejk, which is e10. On solving, the first element from the second row gets eliminated. Then k will become 1. We'll multiply e01 with the multiplier constant, subtract it from e11, and we'll update the second row again. This process of multiplication and subtraction will continue for every element of the second row. So at last, the value of k will be 3, which will update the fourth element in the second row. With it, the first iteration of the J loop comes to an end. This indicates that the second row is updated successfully. Now, the value of j equal to 2, which refers to the third row of the matrix. We will again calculate the multiplier constant. So eji, which is e20, equal to 4, and eii, which is e00, equal to 1. On dividing, the multiplier constant equal to 4. This time, k loop will perform operations on the third row. We will again start with k equal to 0. We'll multiply eik, which is e00, by the multiplier constant, and subtract it from ejk, which is e20. On solving, the first element of the third row gets eliminated. Then k will become 1. We'll multiply e01 with the multiplier constant, subtract it from e21, and we'll update the third row again. We will perform these same operations on the remaining elements. At the end, every element of the third row gets updated. With it, the J loop comes to an end. This is our updated matrix after the first iteration of I loop. In the second loop, the value of I will be equal to 1, which refers to the first row of the matrix. The value of j will be equal to 2, as the for loop ranges from I plus 1, which is 2, to len e, which is 3. So the j loop will run only once. Here, j equal to 2 refers to the third row of the matrix. Now we will calculate the multiplier constant. So eji, which is e21 equal to minus 1, and eii, which is e11 equal to minus 1, on dividing, the multiplier constant equal to 1. The k loop will perform operations on the third row. Remember that the value of k will range from I to len ei, as I equal to 1, so the value of k will range from 1 to 3. At first, k equal to 1, so we'll multiply eik, which is e11, by the multiplier constant, and subtract it from ejk, which is e21. On solving, the second element of the third row gets eliminated. These same operations will be repeated on the remaining elements. At the end, every element of the third row gets updated. With it, the J loop comes to an end. This is our updated matrix after second iteration of I loop. In the third loop, the value of I will be equal to 2, which represents the third row of the matrix. This time, the J loop will not function as the condition of the for loop gets violated. The for loop ranges from I plus 1, which is now equals to 3, to len e, which is also 3. Therefore, the loop will break and none of the operations will occur. Hence, this updated matrix is our required output. We can represent this matrix in the form of equations as shown here. We will pass on this matrix to the next function. To make things less confusing, let's outline the steps we'll be following next. These are our equations in simplified form. First, we will solve the last equation to find the value of variable z, which comes out to be 5. Next, we'll use this value of z to solve the second equation, giving us the value of y, which is 20. Finally, using both y and z, we'll solve the first equation to find the value of x, which is 10. Now let's perform these steps in Python. This is the complete code for the solve-elimination function. Let's understand how it works. Here we will input the E matrix, which was returned by the eliminate function in previous code. First, we create a zero array to store the value of the variables x, y, and z. Its length will be equal to the number of variables, which is 3. But why 0? You will get the answer later in the video. Following the bottom-to-top approach, we start with the last row and move upward through the matrix. The variable I is used to iterate over the matrix row by row. Initially, I equals 2, which refers to the index of the last row. The value of variable j is equal to 2. It stores the index of the second-to-last column in the matrix. This is because in the last row, only the coefficient in the second-to-last column is non-zero. J will help us to perform necessary computations. We use the condition of I greater than -1 in the while loop to ensure that I includes 0 index and does not become negative. Now, we extract the last row from the matrix and store it in a variable named row. The sum adds up the parts of the equation which involve variables we've already solved. You will understand more about this in the next iteration. The value of k ranges from j plus 1 to length of row minus 1. Here j plus 1 equals 3, and len in row minus 1 is also equal to 3. Therefore, the condition gets violated and the k loop will not be iterated. To calculate the values of the variables x, y, and z, we subtract the sum variable from row minus 1 and then divide it by row j. Here, row minus 1 refers to the last element in the row, which represents the constant term of the equation. Row j refers to the coefficient at index j in the row. Therefore, we subtract the sum variable from row minus 1 and then divide it by row 2 to calculate the value. Thus, solution 2 comes out to be 5. Hence, the value of variable z equals 5. We will reduce the value of I by 1 to consider the second row this time. So I becomes 1. We also reduce the value of j by 1, so j becomes 1. Now, the row variable contains the second row. We initialize the sum to 0. This time k ranges from 2 to 3, so this loop will run only once, and the value of k will be 2. This formula is used to update the value of sum. It helps add up the parts of the equation that involve variables we've already solved. As we have already solved the variable z in the last iteration, so here we multiply row 2 by the solution 2 and add the value to sum. To calculate the variables, we subtract the sum value from row minus 1 and then divide it by row 1. Thus, solution 1 comes out to be 20. Hence, the value of y equals 20. We will again reduce the value of I by 1 to consider the first row, so I becomes 0. We will also reduce the value of j by 1, so j becomes 0. Now the row variable will store the first row. We again initialize the sum to 0. This time k ranges from 1 to 3, so the loop will run twice. This means we will calculate the sum twice. In the first iteration, the value of k is 1, as we have already solved the variable y in the last iteration. So here we multiply row 1 by the solution 1 and add the value to sum. In the second iteration, the value of k equals 2. We take the previous value of sum and update it by adding the product of row 2 and solution 2. This gives us the required value of sum. To calculate the last variable, we subtract the sum value from row minus 1 and then divide it by row 0. Thus, solution 0 comes out to be 10. Hence, the value of x equals 10. Now we have the value of each variable, and this becomes our final solution. This is the complete code to automate the implementation of elimination method, which we discussed in the beginning of the video. You are already familiar with the 2 blocks of code on left side. Now let's discuss the other 2. Here, we are defining the E matrix which we introduced earlier and inputting the same to the solve function mentioned above. The solve function plays the most important role here. it calls the eliminate function with e as the input, which performs the operations and returns the updated matrix. This new matrix is again termed as e. At the end, it calls the solve-elimination function, which performs the operations over this new matrix e and returns the solution matrix as output that contains the values of variables. Hence, our goal is completed here. You can also try to implement the same with different equations. Now here are some questions for you. Try solving them and post your answer in the comments. That's all for this video. In the next video, we will cover quadratic interpolation, showing how to solve a problem and predict values using curves. Stay tuned.